Hello everyone. Welcome back to Daily Coding. Today is day 44. Today is a Friday at 11 p.m. So recently I've been doing these dynamic programming questions, and I feel like I'm kind of struggling with them. So I definitely want to come back and revisit them and make sure I do them the right way and kind of, really get used to the way of thinking for dynamic programming. So today I'm going to try a different section. So I'm going to go to this greedy section over here and try a problem from here. So let's look at maximum subarray. I haven't looked at this one. So before I start, so my understanding of greedy problems is that at every sub problem you pick either like the maximum or minimum possible choice that gets you close to the answer, the final answer. And you assume that that will work. So like you assume that the most greedy choice in the sub problem, and greedy as like closest to the end problem, is the solution of every sub problem. I don't know if that's right. That's my understanding going into it. I don't know if that's accurate. So let's see if we can use that line of thinking or do something else for today's problem. So maximum subarray. And if you see me alt tabbing, I have to check my mic. Given an array of integers nums, find the subarray with the largest sum and return the sum. A subarray is a contiguous, non-empty subsequence of elements within an array. Okay, so let's look at the first example. So pretty self-explanatory, basically. Look at the subarrays and just return the one that has the max sum. That's what the question's asking. So here we can see that the largest sum is from here 4, -2, 2, 1, -1, 4. Okay. So a brute force solution to this problem would be if you start with a sum of 0. Okay, so a brute force solution to this problem would be you get all subarrays, calculate the sum of all of them, and return the one with the largest. We also don't need to return the subarray itself. We just have to return the sum. Yeah, so I feel like this doesn't seem too bad. But yeah, so for instance, the brute force, let me just write down the, so 2, -3, 4. Was it -2, 2, 1, -1, 4, I think. Yeah, okay. So if this is our array, we want to return the subarray that has the maximum sum. And it has to be contiguous, so we can't skip like the other subsequence problem. Okay, so if we start with 2, we basically have, okay, how would I generate all subsequences? Because normally it's like you either include it or you don't. But in this case, I guess we either start at 2 or we don't start at 2. Or maybe it's not even a decision tree. It's just like the first subarray is everything. Well, okay. So even though I'm not going to solve it like this, I still think it's good for me to know. So how would I generate every subarray? Okay, so let's look at a more simple example. So here, 1, 2, 3 is a subarray. 1 is a subarray. So let me write all of them here. So here's our input. So we have 1, 2, 3 as one array. We have 1, 2 as an array. We have 2, 3 as an array. We have 1 as an array. We have 2 as an array, and we have 3 as an array. And that's it. No. Yeah, yes. Yes. But okay, but they're not. I just want to draw them all on the same level. I feel like would help me visualize it. So it's almost like you're choosing it with the added exception that it has to be contiguous. So I could generate all subsequences by at every number you have a choice of whether to include it or not. But in this case, we have the added like stipulation, I guess, that it has to be continuous. So if we start with empty list, we can either include the one or not include it. And then after that, so if we choose empty at the beginning, okay, so then we can either include the 2 or not include the 2. And then here, same thing. So 1, 2, or don't include it. And then we can either include the 3 or we cannot. So this branch here is actually not possible because it's separated by a 2. And then this would be, we don't include it. All right, and then here we have 2, 3, and here we have 2. And then here we have just 3, and here we have empty list. Okay. So the only one that's not possible here is 1, 3. Everything else is possible. So the shape of this is we choose not to include something and then to include something. Now, you might say we're choosing not to include something and then to include something here, but the difference is it's an empty list. So whenever we choose not to include something, so I'm noticing there's almost like different start points. So these are the start points. So if we choose not to include something, then this is the end result. So it's basically like the start point. Okay, so let's redefine this now. So it's like each one could be a start point. So I think it might be more of like an n squared type thing. So you have your start points, which is every number. And then you can either keep going or stop at this start point. So for 1, for instance, we can either have just 1, we can have 1, 2, and then stop, or we can have 1, 2, 3, and then stop. With 2, we can have 2 and stop, or we can have 2 and 3 and stop. And 3, we can just have 3 and stop. So this kind of reminds me of like just a 2-pointer. So you have I, and then J, I guess, like here. So, okay, this is one combination, this is another combination, this is another combination, and then I goes up, J goes to I. This is one combination, this is another combination, I goes up, J goes to I, this is another combination. So you take the kind of the window between I and J, and that's how you would get a subarray. Okay, so that being said, I don't think we actually want to do that because there's other ways we can use the fact that we always want to get the largest sum to kind of make informed choices at every subproblem. So for instance, if we have a 2 and a -5, we're probably not going to include this -5 because it brings down our sum. Unless, I suppose, okay. So let's say there was a 9 here. So from the 2 point of view, if we had to start at 2, it would make sense to include the -5 because we also need the 9. But if the sum of this is -3, we might as well just start at the 9 and just get a total of 9 instead of 9 minus 3. Wrong red. Instead of 9 minus 3. So I'm guessing whenever we obtain a negative number, or not necessarily a negative, but a number that we could do better than, that we've seen higher results, we can just discard it. So for instance, let's kind of let's muscle through the input here. So we have 2, -3, 4, -2, 2, 1, -1, and 4. Okay, so here at 2, so this is the max. So we're going to keep track of the max that we've seen so far. So here at 2, so we'll start at I equals 0. So at 2, so far we found a subarray that has a max value of 2. So that's our max, and it's just this one. Okay, so now we can go to, let me get rid of the brackets there. Okay, there we go, and 2. Okay, so now we can include 3. So it's basically asking, should we include 3? So our current sum now would be 2 minus 3, which is -1. So because that is less than our previous, then our new sum maybe then should just be 0. So so when we go to our next number, we want it to just be this number, like to check. So we know that out of here, our highest sum achievable was 2. So now we kind of reset the problem and see, can we do something better in here that's better than 2? Okay, so then we'd see, okay, this is 4. We say, okay, this is 4. So max is now 4. And then we move I. Okay, so now that we see, so now we're at our sum, our current running sum is 2. So what this means is it's advantageous for us to include this part, because whatever is in this, we're just going to add this 2 to it. So we want to include this as part of our subarray. Whereas in the other case, it was -1, so that's disadvantageous, or I don't know if that's a word. But we don't want to include it in the rest because this discounts. But here, 2 actually adds, so therefore it's beneficial to include. So hopefully that makes sense. So we'll, I guess we would need to remember what pointer we're at for our left. Okay. And then we go here and our sum is 6. So that's good. That's our new max. Different color every time. And then 3. So now our sum is 7. And that's also our max. Okay. And then it's 6. So we go back to 6. So as of now, this is the best. So like in our max, we want, well, I guess we don't need the subarray itself, but if we did, we would also remember this one. So like whenever we update max, we would just store left and right. But we don't need that. Okay, so then we go to 6. So as of now, this is still advantageous to have because whatever comes after it will get a bonus of 6. And then we get to 4, so then it's 10, which is not the final answer. So I might have something wrong here. 4, -2, 2, 1, -1, 4. All right, let me recalculate it. So 4 minus 2 is 2, plus 2 is 4, plus 1 is 5, minus 1 is 4. Okay, I must have made some arithmetic mistake here. So it's, I think I did 4 plus 2, but it should have been 2 plus 2 here. But same logic. Okay, so that seems, so to define it more rigorously, while we have a positive number as our sum, we should keep going. When it's negative, we should update our left pointer. Or if it's negative, just make it 0. Because we don't actually need the pointers. So what I'm saying is like, okay, so we determine this is -1. So instead of adding this, we can just not include it at all, which would be 0. So we can reset it to 0. Okay, so now my question is, what if it's all negative? And it has to be non-empty, right? Non-empty, okay. So what if it's now all values that are negative? So let's say we have this here. So we can tell, let me add -6 here. And then we don't need that. Okay, so we can tell by looking at it, to maximize our sum, we should pick the lowest negative value. So algorithmically looking at it, So what we would do is, okay, I think it's the same algorithm actually. So we'd store our max as negative infinity to begin, and we started with I equals 0. Okay, that's a 6. So that's our biggest max that we've seen so far. Because it's negative, we're going to reset our sum to 0. So it's basically like we don't really want to include this when we calculate the rest of the problem because this doesn't help us because it's negative. Okay, so then we go to negative 2. So sum plus negative 2 is negative 2, and that's a new max. And then, okay, we don't want to include this because it's negative, so we do 0. And then we go to 5, we get negative 5, it's negative, so we reset it to 0, and etc. Okay. And even negative 1 by itself, I think would also work. So if this is our list here, so I equals 0, and it's going to be the biggest thing that we found. Okay, so basically we're just going to iterate through. So I'm going to try coding this, and then if I run into any problems, then we can address them there. So let's look at the edge cases here. So we can have a length of 1, and it can be negative 1,000 to 1,000. Okay, so I believe this algorithm would be O of n. So let's try it. So we'll call max. What should I call that variable? Largest, I guess. And we'll set that to negative infinity. So no matter what, the first element we encounter will be bigger than this. Okay, so for I in range, length of nums. All right, still not muted. Typing too quickly. Okay. And then we'll also have like current sum, which will be 0. Okay. So we're going to say current sum equals plus equals nums of I. Right? So we start with 0, and then we're going to say, okay, our new sum is 2. And then we're going to update the max. So we'll say largest equals the max of itself and current sum. And then what we're going to say is if current sum is less than 0, then we should set it to 0. So like we don't really want to include the negatives like I was saying. So we're just going to reset it back to 0. Is there anything else that I need to add? So we're going to add current sum. So what if it's not 0? So if we have like 1, 2, 3. So here current sum will be 1, and that's the biggest. And then we want to include that 1, so we'll add 2. Now it's 3. So we're basically just taking the sum and then resetting if it's negative here. 3, that would be 6. Okay, so instead of overthinking it, I'm just going to run it and see if I get anything wrong. And I didn't return anything, so that would make sense. So let's see. Okay, so we got the test cases accepted. All right, great. Awesome. Yeah, I think that's something I'm trying to work on with programming is balancing thinking too much and thinking too little. So I think I have a tendency to overthink problems instead of like trusting intuition. So I was about to sit there and trace the whole thing with this example, but I didn't feel like I had to do that, and I wanted to kind of trust my intuition a little bit more. So I just ran it, and it looks good. So this is obviously O of n. Actually, very simple algorithm. I guess it is a medium problem though. And yeah, this is usually I have my second monitor, so I can run it on LeetCode, but I'll just do it, I guess. Okay, so it's called maximum subarray. Because sometimes with NeetCode, I'll get it accepted on this website, NeetCode, but not actually on LeetCode. So let's see if it gets accepted. So I'll just run it like that. Okay, perfect. pretty decent solution. I feel good about that, actually. I was losing a lot of confidence with the dynamic programming questions, but I feel like I did this one pretty good. I had a good thought process for it. Yeah, so thank you guys very much for watching. Today was day 44. Little late recording today, and I'll see you all tomorrow for day 45. Thanks.